everyone for coming to the seminar today, despite in the lockdown. Hope everyone is doing well. So today's speaker is Dr. Samitha Evistigala from Augmented Human Lab. He recently obtained his Ph.D, right? It was last month, was it? Or
yeah, it was last month, yes.
Yeah, so I was the H.O.D nominee for his PhD defense, and it was easily one of the best that I attended, actually. So if you look at his reviewers' comments, you don't usually get a professor saying that he learned a lot from a PhD thesis, but this is exactly what one of the reviewers said. And another interesting commendation was the fact that Samitha took a risk and worked on a truly fun project. So I'm sure you will all see what he meant by this by the end of Samitha's project. So without any further ado, let's invite Samitha to start his presentation. Samitha.
Yeah, thank you so much, Vicky, for the nice introduction. So today I'm going to present my PhD research uncovering the potential of the foot for novel input-output interfaces. So do you know what the world's first wearable computer is? Yeah, actually the world's first wearable computer is considered as an instrumented shoe consisted of a toe-operated switch with a wireless module. It was used by two MIT researchers, Edward and Shannon, to predict the outcome of a casino roulette inconspicuously. The ease of integration and the discreteness can be considered as the two main reasons that they used a shoe-on interface. And most importantly, the shoes are something that already available to all of us. So it would have been easy for them to integrate electronics into it to use as a wearable computer. Although the world's first wearable computer is a foot-worn interface, most early foot interfaces are not wearable. They were designed as stationary input devices for hands-free interactions. For example, this photo shows a knee-operated device that can be used as an alternative for a mouse. So most of the early foot interfaces can be divided into three categories: foot-worn, foot tracking, and foot-operated interfaces. However, the advances of ubiquitous computing slowly transferred the foot-worn interfaces into human augmentation devices. The human augmentation devices that seamlessly integrate with the user's mind, body, and behavior are considered as assistive augmentations. And by looking at the literature, I identified that both foot interfaces and assistive augmentations have clear overlaps. And I named interfaces at this very intersection as augmented foot interfaces, or simply as AFIs. So in my research vision, I defined this new paradigm of foot interfaces as self-contained foot-worn mobile interfaces that extend human abilities with sensing or output capabilities. So AFIs enhance human capabilities in three ways. First, by sensing physical parameters, or in other words, acting as an input device. Secondly, by providing feedback to the wearer, or acting as an output device. Finally, by using a combination of sensing and feedback. So in my research, my main goal is to show the potential of the foot for novel input-output interfaces. To do this, first I started looking at prior work that I can classify as an augmented foot interfaces. So I classified over 100 academic publications and commercial devices starting from 2003 to 2020. And this is the taxonomy that I proposed for augmented foot interfaces. So after classification, I identified several unique opportunities that AFIs provide in answering several challenging problems in human augmentation. Firstly, AFIs are immediate. They can easily be designed for any footwears, and footwears are readily available to all of us. I'm sure even at this moment, some of you guys might wearing some sort of footwear. So hence there is an opportunity to design AFIs available immediately, anywhere, anytime. Secondly, they are discrete. AFIs can be easily hidden inside our footwears. So this is the quality that used by Edward and Shannon in their casino problem. Most importantly, they can be used to sense important biomechanical parameters such as center of pressure and gait parameters such as walking speed or step time. Not only detecting biomechanical parameters, but also AFIs can be used to detect behaviors by sensing the features of involuntary foot gestures. Also, foot is densely populated with high sensitive nerve receptors. Hence, it is easy to design subtle but efficient feedback devices for the foot. Finally, it can be used as a multi-purpose interface. Again, shoes are something we daily wear. Hence, designing AFIs around shoes will ensure that they can be used in various daily applications that need to sense physiological, behavioral, and context parameters. So as I explained earlier, the main goal of my research is to show the potential of the foot for novel input-output interfaces that supports my vision in augmented foot interfaces. For that, based on these identified opportunities, I explored 3 novel augmented foot interfaces. So in coming slides, I will explain how I investigated the potential of each AFI during my PhD research. So first, let's start with stress foot, which is an input AFI to see how I uncover the potential of the foot for acute stress sensing. So let's talk about the concept behind this idea first. In forensic science and psychology, body language study is already being used to detect people's mental states. Analyzing facial expression is the most common body language technique that people have been using for decades. However, according to research, body expressions are considered as powerful as facial expressions, and sometimes it can even be used to detect deception. For example, a former FBI agent and a famous psychiatrist, Joe Navarro, once said that involuntary foot gestures might be instrumental in detecting deception. So motivated by this idea, I wanted to investigate whether we can develop an AFI that discriminates acute stress and relaxation by using foot movements and posture characteristics. For that, first I conducted a pilot study to identify main foot pressure and motion characteristics that change due to stress. So from the pilot study, I identified 4 such characteristics that we can use to distinguish acute stress from relaxation. One characteristic is foot pressure, the center of pressure, and the foot leg posture. And the final characteristic that I identified was foot tapping or foot shakings. So next, I developed a prototype that can sense the variations of those characteristics. The prototype mainly consisted of a pressure-sensitive insole and an inertial measurement unit. Then I conducted a study to develop a model to detect acute stress using the features that I defined from each foot characteristics. For example, from foot pressure, I extracted forefoot pressure, rear foot pressure, and total foot pressure. From center of pressure, I extracted center of pressure x-axis as well as center of pressure y-axis. To get an idea about the posture, I extracted x-axis acceleration, y-axis acceleration, and z-axis acceleration. To identify foot shakings and foot tappings, I extracted median frequency and dominant frequency. So this is the summary of the study design for model development. In this study, I asked participants to perform 2 stress tasks and 2 relaxation tasks. The stress tasks were Stroop color word test and 10 Minesweeper games. The 2 relaxation tasks were an entertaining Minesweeper video and a nature video. Also, I collected participants' foot pressure data, accelerometer data, as well as skin conductance data during each task. After each task, I asked participants to rate their level of stress, level of arousal, and level of pleasantness on a 7-point Likert scale. Additionally, I also asked them to fill a NASA task load questionnaire to get an idea about the task load. These measures helped me to confirm that the participants were under stress during stress tasks as well as they are relaxed during the relaxation tasks. So this is the summary of the probes that I collected and the summary of the skin conductance data. You can see on average, participants were stressed during stress tasks and they were relaxed during relaxation tasks, confirming that they were in the intended states. So then I started developing models. I developed several models using each feature that I identified earlier, also developed several models combining different features. So this is how models behaved during each task. And this is a summary of the accuracy levels of each model. So my best model was able to detect acute stress with an accuracy of 85%. I conducted another study to validate the generalizability of my models. For that, I recruited 11 new participants who did not participate in the previous study. So in this study, I asked participants to perform a new stress task, a mental arithmetic test as a relaxation task. And also I asked them to look at a relaxing nature video as a relaxation task. Similar to study one, I collected foot pressure data, accelerometer data, and skin conductance data. Also, after each task, I asked participants to report their stress level, arousal level, as well as level of pleasantness in a 7-point Likert scale. Additionally, I asked them to fill the NASA task load questionnaire. So you can see in this study also, on average, participants were stressed during stress task and were relaxed during the relaxation task. So this is the summary of how models detected stress and relaxation during each task. So in this study, my best model distinguished acute stress with an accuracy of 87%, including an F1 score of 86%. So finally, I conducted an in the wild study to confirm the external validity of my models. For this, I asked participants to wear the pressure insole and the accelerometer in an 8-hour working day. Similar to previous studies, I collected foot pressure, accelerometer data, as well as skin conductance data. So after completing each hour, a reminder was sent to answer the same questions that I asked in previous studies. The results showed a significant correlation between self-rated stress levels and the model-derived stress levels. So from this series of studies, I developed the model, validated the generalizability, and finally tested the robustness of the models in the wild. To summarize the work in this direction, I created a small video. So let's look at it first before moving into next projects.
Samitha, we can't really hear the audio.
Oh.
Maybe put your microphone near the speaker on your laptop or machine.
Give me a second. I'll do it. Not sure if I.
For participants.
Can you hear now?
Yep.
Afterwards, we made them relax. We observed that acute stress resulted in an increased forefoot pressure, a shift of center of pressure towards the front, and a different foot-leg posture. Some users also demonstrated a nervous foot tapping while being stressed. Over time, the average electrodermal activity raised when the user was set under acute stress. In a relaxation task, the electrodermal activity dropped again. We developed several machine learning models that are capable of detecting both stress and relaxation to construct the validity of stress foot. We achieved reasonable accuracy rates for these 4 foot characteristics. To also demonstrate external validity, we conducted an in the wild study with 10 participants, performing their usual everyday office tasks over a working day. Our models demonstrated substantial robustness. To sense stress with our technique, we can upgrade any existing smart shoe or smart socks. Also, other form factors are feasible, such as a small sensor tag, or utilizing an existing pressure floor. For more information, please refer to our paper.
So this entire work I published in Census Journal. So I didn't stop here, since this is a novel method of stress sensing, and there are many other methods to detect stress. I wanted to investigate a compelling application that uses the unique advantages and limitations of our stress models. So one of my method's main advantages is that an IMU-based model can already provide 86% of accuracy. Hence, any off-the-shelf IMU sensor tag can be used to detect stress. Also, the models were trained to detect stress during sedentary office tasks. So using these qualities of my models, I proposed a do-it-yourself toolkit for self-tracking stress during sedentary office tasks. The toolkit utilized an off-the-shelf IMU sensor tag that could attach to your shoe. By using a companion mobile app, IMU data of the sensor can be streamed to our models to detect stress. Also, users can define their own stress interventions according to a threshold stress value. To facilitate number of stress intervention possibilities, I even connected our companion mobile app with if this then that platform, also known as IFTTT. To summarize this work behind Stress Shoe, I created a small video. So let's take a look at it.
According to the World Health Organization, work-related stress is considered one of the most common health problems. Self-stress tracking at work is an essential aspect of stress management and is often the first step to improving mental health and personal well-being. Although there are many methods to track stress, systems for managing stress is yet to be explored. As a solution, we present Stress Shoe, a DIY toolkit for just-in-time personalized stress interventions for office workers performing sedentary tasks. We adapted a method to track stress, based on foot posture and motion characteristics by using an off-the-shelf IMU sensor tag, connected with a companion mobile app. A focus group study and a pilot study informed the mobile interface design for stress tracking and personalized stress interventions. After connecting, the sensor needs to be calibrated. Then users can select the stress level and the logic of the condition to trigger an intervention. Finally, interventions can be selected. Users also can define interventions to control the sitting time. It also provides the option to connect with the IFTTT platform, enabling users to create many custom interventions. Moreover, for self-stress awareness, a visualization of daily stress log is also provided. To demonstrate the benefits of our system, we evaluated Stress Shoe with 10 users over 4 weeks. They were provided an IMU with 4 enclosures, which enables attaching the IMU to shoe in different ways. Users created personalized interventions and found that Stress Shoe is easy to use and helped them reflect on their daily stressful experiences. Some of the example applications they created are changing wallpaper to control the ambient environment, turning on relaxing music to create distractions,
How the rain doesn't make you dance when you jump with your friends at a party.
setting reminders for new routines like having a coffee break, or notifications for self-motivation. Users found that setting reminders for new routines are one of their most preferred intervention methods. For more information, please refer to our paper.
Yeah. So this work has been accepted for mobile CI 2021. So now let's move on to the second project where I developed an output AFI tickle foot. In this project, I designed, developed, and evaluated novel foot tickling mechanism that can evoke laughter. So first, let's look at the concept behind this project. There are two types of tickling. The first one we call nismesis is basically an itching-like sensation, which we feel when our body is lightly touched, and it does not evoke laughter. And also, it's self-inducible. The other type of tickling called garglesis, which I am sure that we all have experienced at some point in our life, it is a heavier form of tickling that evoke laughter. But not like dysmesis, garglesis is not self-inducible, which means it's interpersonal and we need to be tickled by someone else to evoke laughter. However, in 1999, Harris and Christenfield showed that garglesis tickling is not only interpersonal, but also a reflection for a heavier stimulation. And they successfully showed that a machine can also tickle. Since then, there were many artifacts which were aimed to tickle, targeting different human body locations, such as wrist, cheek, hand, arm, even soles of the foot. However, many of those artifacts were not rigorously evaluated to check whether they could evoke laughter. So in this work, I wanted to explore this primary research question: can we design a tickling artifact for the foot that can evoke laughter? According to Charles Darwin and other literature, foot sole is one of the most ticklish body locations of the body. Also, it has a large concentration of highly sensitive nerve receptors. Next, I wanted to design an activation mechanism. Prior tickling artifacts targeted to evoke laughter mainly used vibration motors, but they were not successful. Hence, in my approach, I designed a customized actuator based on magnetic levitation technology. It has 4 PCB coils that can move a brush-mounted magnet in different directions. I mainly actuated the magnet in 2 patterns, straight and circular, and each pattern actuated in 3 frequencies. Next, I wanted to identify the most ticklish locations of the foot. So in this study, I used a separate platform that allowed to tickle a specific location of the foot sole. So from this study, I identified 3 locations that significantly ticklish compared to other locations. So we found the most ticklish areas are closer to the arc region of the foot or the foot arc. However, I didn't select the foot arc as one of the tickling locations, since some people may have a profound foot arc. In the next study, I wanted to adjust the parameters of the stimulation pattern. So I recruited another 14 participants and asked them to keep the foot on this customizable test bed. And then I provided 18 different stimulation patterns for each foot and both feet together. From the results, I identified that when I stimulate both feet using the circular pattern with 2.4 Hertz, the participants rated the highest ticklishness. I also took a measurement called 5-point behavioral scale that rates participants' reactions to the stimulation. This scale was mainly used in prior research in related to tickling. So you can see from the graph, in general, the stimulation BCF2 evoked laughter. So I identified that BCF2 as our tickling pattern that can evoke laughter. Finally, I wanted to further confirm that our identified pattern can successfully evoke laughter, and also I wanted to check what type of emotions that it can elicit. For this study, I recruited another 12 new participants who did not participate in our previous studies. The results showed that the stimulation significantly rose the number of skin conductance peaks as well as the skin conductance levels compared to the baseline, confirming an emotional arousal. Also, in a post questionnaire in general, participants rated that during stimulation, they experienced a higher valence and a higher arousal. 5-point behavior scale also confirmed that in general, participants were laughed during stimulation. Also, I asked participants to describe what they felt during the simulation. The majority of the participants used the word tickling or ticklish to describe the stimulation and used the word fun as an adjective. So these findings reveal that I can use our tickling simulations to evoke laughter. Finally, I wanted to show the possibility of a wearable tickling interface. So I designed an insole integrating 3 tickling actuators in the identified locations. The insole had several layers at the bottom. It has a flexible aluminium heat dissipation layer. On top of it, it has a flexible Ninja Flex layer that integrates PCB modules and cables. On top of it, I included some protection layers, a flexible silicon layer and a Ninja Flex layer that protects participants' feet from wires and PCBs. Finally, I gave a prototype to several participants And this is how they reacted to our prototype. You can see they are laughing and having some fun. Finally, by analyzing the participants' feedback and prior work on psychology of tickling, I derived 3 application scenarios that our tickling insole could be used. Number 1 is we can use it for remote playful interactions for couples. The second application is eliciting mirthful responses for entertainment, like in 4D cinemas, and creating distractions to release stress. So before go further to summarize this work, let's look at this video.
A novel foot tickling mechanism that can evoke laughter by creating tickling sensations along the sole of the foot, utilizing magnet-driven brushes. At first, we developed an actuator that can drive brushes mounted on magnets. Then we conducted 2 studies investigating the most ticklish locations and stimulation patterns that provide tickling sensations to evoke laughter. We selected the pattern with a significant self-rated ticklishness. In a follow-up study with a new set of participants, we confirmed that the identified stimulations could evoke laughter. Finally, we embed our actuators into a flexible insole, demonstrating the potential of a wearable tickling insole. Participants' feedback implied that TickleFoot would be useful in playful interactions connected with fun and laughter, such as remote interactions between loved ones. Eliciting mirthful reactions for entertainment. By changing the end effector, the device can also be used as a foot massager for relaxing, or even for releasing stress. For more information, please refer to our paper.
Yeah, so this work is under revision stage for Tokai journal. So let's move on to my final project, Gym Soles, which is an input-output AFI that can use to improve squats and deadlifts by visualizing the user's center of pressure. First, let's look at the concept behind Gym Soles. So when you perform full body exercises like squats and deadlifts, your upper body posture is changing. However, all our body's weight and impact forces are going through our feet. Hence, the changes in the upper body posture will change the foot pressure profile. Thus, there should be a relationship between your body posture and the plantar pressure profile. Imagine you are performing squats with an incorrect upper posture. You should be able to identify it by looking at your plantar pressure profile. Building upon this concept, I started to explore this research question: can we improve exercises such as squats and deadlifts while only visualizing the plantar pressure profile? So to explore this research question, first I interviewed 4 trainers. So according to them, full body exercises such as squats and deadlifts are very important, and they typically used center of pressure as a reference point when training those exercises. From these interviews, I identified several requirements for an AFI that can use to improve exercise postures when performing squats and deadlifts. Number 1 is it should sense a biomechanical parameter that reflects the body posture while exercising. I identified that parameter as the center of pressure. It should have an appropriate feedback mechanism that can display the center of pressure in real time. So that's the second requirement. So I started developing our prototype. My prototype is, as my input, I have an off-the-shelf pressure sensing insole with 16 pressure sensors. From these 16 pressure sensors, I calculated center of pressure by taking weighted average pressure. Secondly, I developed 2 output mechanisms, vibration and visual. Vibration feedback used 8 vibrotactile motors and attached to the slide wall of a shoe. Those motors vibrated in a way that you feel where your center of pressure is. For example, let's imagine that your center of pressure is at your heel area, the motor number 3, 7, 4, and 8 will vibrate. Since center of pressure is much more closer to the motor number 4 and 8, those two motors will vibrate in a higher intensity compared to motor number 3 and 7. The visual feedback system is a Java-based software which shows your center of pressure via a monitor. Then I conducted a study to test whether our prototype could significantly improve body posture. I recruited 4 trainers and 13 participants for this study. First, I asked 4 trainers to perform squats and deadlifts under an OptiTrack motion tracking system. I collected their foot pressure profile, foot pressure data using my prototype, as well as motion data using the motion tracking system. This data I considered as our gold standard or the ground truth. Secondly, I asked 13 participants I recruited to perform squats and deadlifts under the motion tracking system. I specially asked them to perform deadlifts with 2 weights, 10 kg and 20 kg. Similar to the trainer's case, I collected foot pressure data and motion data. Also, I asked participants to perform these exercises under 3 feedback conditions: no feedback, vibratactile feedback, and visual feedback. All the conditions were counterbalanced across participants. Finally, I compared the center of pressure each conditions. You can see when users having the feedback of center of pressure, they were able to keep the correct center of pressure profile that is similar to the trainer's pressure profile. So only no feedback is significantly different to other pressure profiles. Also, from motion tracking data, I extracted knee angle to hip angle ratio that basically provided me an idea about participants' posture. Here, I first show the results for all the participants. You can see only in deadlifts 20 kg, I can see a significantly improved body posture, and it's similar to the trainer's body posture when they having either feedback as vibratactile format or visual format. So in other 2 scenarios, it's difficult to come to a proper conclusion. Then I divided my participants into 2 groups: beginner level participants and advanced level participants. And first, let's look at the data of advanced level participants. So I considered advanced level participants as people who have done these exercises before, and most of them regularly perform these exercises. You can see they already good at these exercises. Even without the feedback, they were able to perform these exercises properly. However, if you look at the beginner level participants who haven't performed these exercises before, you can see in all the exercise scenarios, when they're having feedback either as vibratactile format or as visual format, they were significantly improved their body posture, and it was similar to the trainer's profile. This concludes the main evaluation of the gym soles. So to summarize the work behind gym soles, let's look at this short video.
We present gym soles, a system which assists users to improve squats and deadlifts by solely visualizing the user's center of pressure. The correct execution of exercises such as squats and deadlifts is essential to prevent bodily injuries. Existing solutions either rely on expensive motion tracking or multiple inertial measurement units-based systems. These systems are considered impractical, requiring extensive setups such as individual calibrations. This paper, therefore, introduces a proof-of-concept prototype, gym soles, an insole system that provides feedback on the center of pressure at the feet to assist users with maintaining correct body posture while performing squats and deadlifts. We evaluated gym soles with 13 users in 3 conditions. No feedback, vibratactile feedback, and visual feedback. Results show that visualizing only the center of pressure contributes to a significantly corrected body posture. Novice users were able to execute these exercises similar to that of an expert trainer.
This entire work I published in CHI 2019. Then I further improved the prototype according to the feedback of my initial participants and trainers. They wanted more unobtrusive wearable feedback, so I developed a vibrotactile insole that can insert into a shoe. Also, I miniaturized my PCBs to improve the wearability, and also developed a peripheral feedback method to provide unobtrusive visual feedback using a peripheral head mounted display such as Google Glass. So let's look at this short video to get an idea about further improvements of gym soles.
Gym Soles Plus Plus, an insole-based system to improve the body posture when performing squats and deadlifts. We developed a flexible wearable insole with 8 vibrotactile motors that provides haptic feedback on the center of pressure of the body. A custom PCB with 8 motor drivers and multiplexers was developed to control the vibrotactile motors. Additionally, we developed a visual feedback system by using Google Glasses. Our previous work has shown that visualizing hidden information on the center of pressure can assist users in maintaining a correct body posture when performing squats and deadlifts.
So this work I recently published in Petra 2021. Let's look at some of the design considerations that I derived for future research in AFIs based on my literature review, as well as my own work in developing AFIs. The first one is a better utilization of the anatomy of the foot. For example, the ankle region is the perfect area for designing sensor bands that can capture movements, or the high sensitivity of foot soles can be used to create unique sensations. So using this opportunity in my research, I developed a tickling artifact. However, there are many other applications that we can utilize for the high sensitivity of the foot, especially in rehabilitation and in application in virtual reality related applications. I have seen many AFIs analyzing physical behaviors like activity, posture, and other physical activities. But when I look at literature, I saw the potential of using a foot-worn interface to detect acute stress. So I used that opportunity to develop several models to detect acute stress and utilize them in sensing acute stress during sedentary office tasks. However, I believe that there is a lot of room available in this direction for AFIs. You can extend these models for other postures as well, like standing. For example, such models can be used for nurses or construction workers who primarily work in standing positions. Also, for some of those workers, wearing shoes are mandatory, so it would be an added advantage to include some of the sensors and actuators and see how we can use this in sensing stress. Although most of the early AFIs were designed for explicit interactions, in my literature review, I identified that after 2000, around 80% of AFIs are designed for implicit interactions, such as gait analysis, activity detection, or posture detection. Even my work, gym soles and stress foot, use implicit interactions. These examples may imply that AFIs are easy to design for implicit interactions compared for explicit interactions. This could be mainly because our foot is primarily used for walking and it engages with the external world primarily as our main tool of locomotion. So it is hard to use our feet for explicit interactions most of the time. However, we can use it for implicit interactions at any time. We can simply sense our physiological parameters or involuntary foot gestures, or use our shoes to detect contextual parameters and use it for applications. So smartwatches and smartphones already act as our companion devices for non-discrete interactions, such as taking photos or performing other hand gestures. In contrast to handheld or hand-worn devices, foot-worn devices capture less social attention due to the location. For example, AFIs has offered unique discrete form factors such as smart insoles or socks, even hidden sensors in smart shoes. This quality can be easily used to design AFIs for discrete computing. Also, I believe a future smart shoe with sensing and feedback capabilities can be used as our discrete companion who senses our physiological, behavioral, and context parameters and provide valuable information to our body to improve our lifestyle. So now let's talk about the summary of contributions that my thesis contributed to the knowledge pool of HCI. Firstly, I have a few artifact contributions. The first one is the stress detection method that I developed based on foot motion and posture characteristics. Secondly, the foot tickling mechanism that I designed and developed to evoke laughter. Third one is the gym source prototype that senses and provides feedback about the center of pressure to improve body postures. So in my literature review, I made a survey contribution classifying over 100 papers in augmented foot interfaces and foot interactions. Also, I evaluated all my artifacts with over 100 participants in a series of laboratory and in-the-wild studies, contributing to several empirical contributions. Finally, I also contributed several design considerations and guidelines for future augmented foot interfaces based on my work. So these are the journal and conference articles that I published for my PhD work. You can refer to these papers if you need more information about my work. So my literature review has been published as a full paper in the Augmented Human Conference 2021, one of the best conferences for augmented human technology. So in that paper, you can find more information about classification as well as some more information about future directions in augmented foot interfaces. The work on gym soles was published in CAI 2019 as a full paper, the premier and the most prestigious conference in HCI. The paper already has about 26 citations. The gym soles plus has been recently published as a full paper in Petra 2021. The paper won the best student paper award. The research on stress foot was published in MDPI Census Journal, and it has 5 citations up to now. The Tickle foot is currently in the revision stage for the ACM transactions on computer-human interaction, one of the best journals for HCI. Recently, the reviewers came back to me with minor revisions. Hopefully, it will be accepted soon. These are some of the first authored and co-authored publications that I worked during my PhD with my other fellow PhD students and researchers. Since this presentation is all about my PhD work, I would like to take this opportunity to thank my awesome supervisors, Professor Surangana Nayakkara, Professor Dennis Mathis, and Professor Thor Bessier. Thank you very much for guiding me in my PhD journey. Thank you very much for that. And also, I would like to thank some of my co-authors in some of my papers. Thank you very much, Shamod, Roger, Loich, Hassel, Johan, and Vipula, for providing me help and support. And last but certainly not the least, I'm pretty much thankful for my lab, Augmented Human Lab, for all the support and help that they gave me throughout my PhD journey. Thank you so much. It's the time for question and answers.
Thank you, Samitha, for the excellent presentation today. Any questions to Samitha for his work? So I'll start first. I've always been fascinated with that gym sole, being a biomechanics person.
Yeah.
So at the moment, it measures the ratio between hip and knee angles, right? You can kind of correlate the foot pressure pattern with the hip and knee angle. Can you, if you put more sensors or have it designed in a different way, can you measure some other important biomechanical parameters, such as like the knee other angles than just the flexion angles? So is it, can it have that kind of resolution in the future? That's kind of
yeah, I mean, I have to say that in the device itself, we doesn't directly measure the knee angle and the hip angle, but we identify some kind of a correlation between those two. Maybe so this particular prototype we developed for squats and deadlifts. So in that, the most important angles are those two angles. But if you look at if you look at some of the other exercises, for example, even an exercise like lunges, there is a possibility that maybe even we can correlate this with the angle of the ankle, which is something that prominent when you perform exercises like lunges. Yes, I think there's a possibility that you can even extend this for those angles as well. And even in Jimso's Paspas, I'm kind of proposing some kind of a method that in addition to the pressure profile, if we can incorporate a simple IMU, we can even identify at what position these participants are in their exercise and provide feedback according to that. So all these possibilities, we can extend our prototype into all these possibilities in future.
Okay, good. So if you have questions, please just unmute yourself and ask question. We are all free to. Yeah, please, Aaron.
I think Aaron has a question.
Yeah.
Thank you, Vicky. Thank you, Smitha. So a lot of the scenarios you've been looking at are either in the home or sort of knowledge work scenarios. I wonder, have you thought about how factories or hospitals or where people were engaged in more vigorous sporting activities like running or skiing, how extensible do you think this type of interaction is beyond very kind of quiet, passive type of environments?
Yes, so definitely there's a possibility that you can extend these applications into those application areas as well. For example, let's say you want to extend this into manufacturing type of application scenario. In manufacturing, most of the people are in standing posture. So definitely there's a possibility that we can identify the fatigue level or physical stress levels. It's not necessarily to the mental stress level, but also the physical stress level, the participants of those users. But there's some challenging problems as well, because in manufacturing, for example, let's say in manufacturing, you can have a lot of machineries which have which works in some higher frequencies. So these frequencies may affect the sensors. So we may have to provide some solutions for those noises, which is possible to provide, possible to do some filterings to filter out those things, and use these use a similar technology to detect physical stress and fatigue level in those applications as well. Talking about some of the other applications, like in ski, I have seen similar applications already in the market, that they use pressure sensing insoles to kind of measure the angles when they do ski, and they use it as a ski training coach. It's very popular at this moment among skiers. So in yes, actually there's a possibility, but in those applications we need to further do some studies and research how other factors affect in detecting these stress levels by using these sensors, because especially, as I said, the high frequency noises in those factories and other scenarios may affect the detection levels. So in that point of view, maybe we might even need some additional sensing, like maybe simply attaching an EDA sensor to the foot, because foot also is a good location to measure EDA changes. So might be a good location to add these sensors as well. But yes, I still have to do a lot of research and study in that direction.
Thank you.
We have one question from the chat box from Musa. He asked, how did you calibrate your motion detection devices and how accurate are they?
Yeah, so the so motion detection devices, it's basically we purchased the off-the-shelf ones, and in the calibration process, especially in the stress shoe, I had certain calibration processes to identify, you mainly have to identify what is the orientation of this sensor, X, Y, Z axis. So if you read the paper, there were 2 steps that participant has to perform, like they have to move their foot for around 10 seconds in parallel to the ground plane. So then the algorithm can identify where your X, Y, Z axis is. So then after that, it's just the machine learning algorithm can detect all these. So I would say we had most of the participants, especially when we do the in the wild study, most of the participants were able to have a proper calibration of the IMU, and some of the participants, actually 1 or 2 participants, were unable to calibrate it properly. There were instances that they did not calibrate it properly, and in that occasions we even reduced the accuracy levels, and that even affected our usability scale and all the other data as well, because they were kind of rating low because of the calibration process was not properly done. However, if you properly calibrated and if you properly follow these steps, it's just 10 to 20 seconds of steps, you can get good results from these models. So in future, we may even able to propose some methods that you can even use the IMU even without calibration. But at the moment, we are using a calibration method, and up to a certain percentage, it worked properly, but there were some occasions it didn't work.
Good. Okay. So any other questions? Oh, okay. Sarah asked, did you look at the position of the trunk as well as the hip, knee, and ankle angles in gym soles? People commonly have a poor trunk position during squat and lift. Yeah. So that's another gym sole question.
Yeah. So so what we observed was, so when you have improper kind of a, if your trunk, especially mainly if your upper body or trunk is not in a proper position, what we observed was basically your knee angle to hip, either hip angle, especially the hip angle, tends to change if your trunk is not in the proper posture. So that's what we observed. So, and that affects the center of pressure profile, and basically it goes to a little bit forward, the center of pressure profile, and that can identify it by the pressure sensitive insole, and it can give the feedback according to that. So my answer is, so even if your trunk is changes, because we were looked at this hip angle, it's actually indicates the changes of your trunk as well. So it's used in that scenario as well. But and in the study, actually, in our study, we always provided the center of feedback. So which means it always vibrates and show where your center of pressure is. But if we have some kind of sensor in your head mounted display, because in GymSource++ we are suggesting a head mounted display as well. So if you have some kind of a IMU in head mounted display, there's a possibility that even a very slight changes of your trunk posture can be identified that by using that IMU sensor, and you can provide feedback according to that. But in GymSource++, we didn't combine those two together, but there's a possibility that you can even identify slight changes of your trunk angle as well.
Okay. Good. So since your new boss, Professor Aaron Quigley, is from the University of New South Wales, why don't you tell us a little bit about what you will be doing in Sydney next month, or when are you going?
I'm still waiting for the visa, so I have to get my medical status. Unfortunately, due to the lockdown, it got a little bit delayed. So yeah, soon, in Aaron's labs, I think Aaron's he's a pioneer of discrete computing. So I will mainly doing developing a lot of sensing technologies and wearable devices in the research direction of discrete computing. So given smart shoes and smart insoles also matching in that theme, I think it will be an exciting journey in UNSW. Yeah.
Okay, Great. Wish you all the best for your
Thank you.
future endeavor. Thank you everyone for coming to the seminar today, and take care, and I'll see you all next week with a new seminar then. Thank you, Aaron, for coming to the seminar again.
Thank you so much.